Hi, my name is Jeff Batchelor. I'm with Silicon Labs Timing Products Application Engineering Team. Today I wanted to share with you some lab techniques to aid in the performance evaluation of timing products, specifically in the area of jitter sensitivity to power supply interference, often called power supply ripple rejection. Because density of each new generation increases, designers are forced to care more and more about the performance of each component when placed in such adverse environments. Since noise and interference are everywhere, and since multiple components share a common power supply, the power supply is a direct path for noise and interference to impact the jitter performance of each device. With jitter pushed to the limit, designers must either relax the density or rely upon timing components that integrate supply filtering, such as Silicon Labs timing products. To ensure proper performance in the system, a designer should validate the performance of the timing components with a power supply ripple rejection test, which I will demonstrate today. Historically, a power supply ripple rejection test, also known as PSRR, characterizes the control performance of linear regulators, but the concept extends easily to the performance characterization of other devices. The fundamental measurement matches what is used for regulators. Simply measure the AC response from the input to the output. In the case of timing, the input is the power supply voltage ripple and the output is jitter. This measurement is the magnitude response of the transfer function. As a matter of convention, the voltage of the input ripple should be constant at all frequencies. Because the supply circuit impedance isn't constant, we simply adjust the input power to maintain a constant input ripple voltage. The actual amplitude of the ripple should be set equal to what you expect to find in your system. For these measurements today, I will use 100 millivolts peak to peak at each frequency. Since the input ripple is applied one frequency at a time, it makes sense to view the output jitter with a spectrum analyzer. The resulting jitter from a sinusoidal input shows up as a sideband spur. The spur frequency is offset from the clock rate by an amount equal to the input ripple frequency. You can see this clearly on the spectrum analyzer. The height of the spurious signal relative to the center frequency, also known as the carrier, is proportional to the percentage of the period consumed by the spur as jitter. Now that we understand the basics behind the measurement, let's examine an actual setup. This setup employs the following elements. A DC power supply provides the average voltage and DC current for the device under test. The DC power supply is filtered through a bias T, which passes the DC current but restricts the AC current. A modulation source provides the voltage ripple. The modulation source is AC coupled through the bias T to prevent the flow of DC current back to the modulation source. A scope is used to ensure that the ripple signal has the same amplitude for every frequency as we discussed. Differential outputs are converted to a single-ended output through a limiting amplifier, which removes noise in common to both outputs, just like a differential receiver in a real circuit. Single-ended outputs can be connected directly to the spectrum analyzer. It should be noted, though, that for the very highest performance systems, differential signaling is preferred because it allows common mode noise to be subtracted, whether the source of the noise is from the supply or other interferers. The output of the differential amplifier is connected to the spectrum analyzer so that the relative spur amplitude can be recorded. And of course, the device under test. First, set the modulation frequency. Second, measure the ripple voltage of the VDD pins at the device under test using the oscilloscope. Third, adjust the ripple voltage to 100 millivolts peak to peak. Fourth, use the spectrum analyzer's marker delta function to quickly measure the relative spur amplitude. Since it is a relative measure, this value is in dB, and a C is often added to reflect that the power is relative to its carrier, hence dBc. Then repeat the steps for each frequency to be analyzed. Once the data is collected, simply apply the conversion from dBc to jitter and plot the results. As you can see, even among crystal oscillators, the performance can vary greatly. In this example, Silicon Labs is 10 times better than the competitive offering. And Silicon Labs is here to help. With integrated power supply filtering and our patented timing architectures, Silicon Labs timing products help you achieve the performance you need for your system. For more information, visit our website and download Application Note AN491. Thanks for watching.